did a fantastic job of summarizing for us the chapter 6 of the book, and that summary is available to you on your Google Classroom. So please do check it out. Your assignment this week also links to your knowledge about the planetary boundaries. But before we go into the talk for today, just a food for thought to keep in mind. So of the 9 planetary boundaries, and as I mentioned, this is information you can find in your Google Classroom, which are the top concerns in your community or your neighborhood or your country? And you could choose the area of focus, whether you want to focus on your immediate physical neighborhood, maybe even your state, whatever you define as the boundaries of your community or your country. Right. And having these questions to think about, we're hoping is going to help to shape your projects further. As Tim mentioned, the licenses have started going out to you so that you can start creating your story maps based on your SDG and your topic of choice. So without going into too much detail, just to give you a quick background on the planetary boundaries. So 9 of them, it is going to be your assignment to find out what they are. But these are the 2 kind of key questions that led to defining planetary boundaries. How can the Earth, which is a finite system, support continuous population growth? And how can we quantify the impact of population growth on Earth's limited resources? So with that background question in mind, in 2009, a group of scientists defined the 9 planetary boundaries. And it is a system, so too much or too little of a particular resource or pollutant can throw off the whole system off balance, right? So planetary boundaries are quantifiable through measurements of pollutants or damages. I'm sure given our current state of the world, we're all aware of what is happening and what is off balance that makes climate change such a huge, urgent, critical concern for us, right? So we are just going to keep that in the back of your mind this week as we go through the different sessions and assignments. And today we have the pleasure of having Dr. Dorothy Peteet with us, who is a senior research scientist at NASA's Goddard Institute for Space Studies. She's also an adjunct professor at Columbia University and directing the Paleoecology Division of the new core lab at the Lamont Doherty Earth Observatory of the Climate School at Columbia University. So now we're really getting to the exciting part of talking to experts who go out there, who, are not just talking about these issues, but who are investigating it hands-on, firsthand. So we're so excited to have you, Dr. Dorothy. Thank you for being with us. And over to you, if you would like to just briefly introduce yourself to the students, and the stage is yours. Thank you.
Sure. Well, thank you all. And thanks for coming and being here and inviting me. I am happy to talk to you. And the most important thing for me is getting your questions. So I'm going to try to go through my PowerPoint pretty fast. Can you see my screen or no? Not yet?
Not yet. Yeah.
Okay. I'll share the screen and start talking about what we do. And oh, sorry. I just wanted to say, I was trained as a botanist. That's what I always loved, plants, but I didn't know what to do with them. So I'm not a good gardener because I feel sorry for weeds. And so I didn't really know what to do with my botanical knowledge. And some of my journey was kind of serendipitous, but I want to tell you about that because I think you should follow what you enjoy doing. So one of the things I started to do when I should say that I found what I could do with plants by going to graduate school and learning about paleoecology and paleoclimate. And so when you take a sediment core, which I'm going to show you, you get a whole history of paleo-environmental information. And the map on the center of this first slide is showing you some marshes. I love the water and I love wilderness. So I was exploring and I saw all of these marshes up and down the Hudson, and they have in them sequestration of pollen grains that can tell you about past climates. And they also have seeds in them, which you can date with radiocarbon and get the age. So you build a story through time. So I want to focus really in this talk on Jamaica Bay. If any of you have been to JFK Airport, it's a marsh right by JFK, and Piermont Marsh, which sits right next to Lamont. So, and this photo on the right there is of an eroding marsh. And I want to tell you how that's really important for understanding carbon and the carbon cycle and what's happening. So a lot of people have helped me over the years. I've been doing this about 40 years since graduate school, and it takes a lot of physical energy to take a sediment core. Here we are out on the islands. If you've never been to a marsh, it's a wonderful place to be. It's usually breezy and there are great birds to watch. I also started a course at Columbia 30 years ago named Wetlands and Climate Change, because I was so excited about what wetlands really do for us. And all these things, they help to treat the water. They capture water. They're like sponges for us. They're nurseries of the whole system in the river because they hide the babies and they give the food chain, you know, from bottom up. So they support birds, fish. Then we protect the shorelines. As you probably know, in hurricanes, the Jamaica Bay really was a protective marsh for the shoreline. And for us, they're important because they're archives of environmental history. But what we only discovered about 10 years ago is that they're also super important for storing carbon. And in fact, wetlands are much more important than forests. And people don't, usually you hear people say, well, you should plant a tree, right? To save carbon, take CO2 out of the air and make a tree. But wetlands are more important because below ground, they're connected to water and they're like a cold refrigerator. So what we wanted to know was, well, how deep are these wetlands and what information can we get from them? And sedimentation means how fast do they accumulate through time? So worldwide, there have been huge losses in wetlands. A lot of people, they have a bad reputation, right? Because people say, oh, they're mosquitoes, or there's a lot of terminology that puts down wetlands. Bogged down, or I'm swamped, right? But actually they're wonderful places because they do all these things for us. And the term blue carbon now is used for these wetlands that are right adjacent to water. So salt marshes, tidal marshes, mangroves are super important all over the world. So they bury carbon 30 to 50 times at the rate of forests. And as you know, forests generally, a tree will degrade and the CO2, because bacteria and fungi break down the tree, it goes back to the air. Whereas if we keep our wetlands, we're sequestering it in the refrigerator, sort of underground. So there have been rules, both nationally, internationally. Some states have a lot of rules in protecting wetlands, but still they continue to be lost at a huge rate. And one of the real important things I think I can try to do is educate people on why they're so important. So these are some of the questions we asked about how they've changed through time and what human impacts have been and how do we save them, basically, and how much carbon do they hold. So there are two parts when you take a core, and that lower picture on the left shows we use this side opening meter long sediment core, and we keep putting extension rods and bringing it up, folding our core up, taking it out of the core, wrapping it up in saran and foil and refrigerating it until we work on it. So you can see what it looks like there. And there are two parts to it. There's the organic part, and organic just means anything that was growing, so plants and animals. Inorganic means the sand, the silt, and the clay that helps to keep the marsh together along with the roots. So what we do is measure how these things are changing through time, as well as the vegetation from the pollen. And I'll show you how that works. And the example I'll use is Jamaica Bay. So Kennedy Airport's this white area B on the map today, but you can see all of this black is a hardened shoreline. In other words, the marsh that used to be there in 1888 and certainly before, which was white, is all gone now. So the only things that's left are these islands, really, blue out here. And we're going to zoom in and look at Joko, which is on the right, and Yellow Bar, which is on the left. Okay. And so many of the marsh area, much of the marsh area has been lost because of dredging or hardening of the shoreline. But the other thing we discovered is that only 8 streams feed into it, bringing sediment now. And there used to be 18. So it's basically starved. And I'll show you how we figured that out. The other thing is there have been aerial photos of the marsh through time, and you can see how as sea level rises, it gets fragmented and eventually disappears. So again, here's the modern, here's the 2 marshes that we chose. And actually next week, we're going to be working on Idlewild, which is over to the right, to compare with Jamaica Bay. So we're still working in this area. Now, if you're a botanist, just like trees have leaves, they also have pollen. And so by learning every tree and plant's pollen, you can count 300 grains per sample. We have to process the samples in the lab, but you build a pollen diagram through time of what was there, and you make percentages of each type. And then I'll show you, you can see what's happening over hundreds and thousands of years. So here's a ragweed. You've probably heard of that. A lot of people are allergic. That's a native plant, but it's also very aggressively comes in when you cut down trees. So it's a marker for European contact. When Native Americans were here, they didn't cut down the forest in huge amounts. Then we have little animals, one-celled animals called foraminifera, which tell us how high in the marsh in terms of sea level rise the area is. Then here's a seed of something of a plant, Salicornia, which grows out on the marsh that we can date and get the age. And we can also get a lot of other information, like the heavy metals, I'll show you, and how much carbon by burning it. And we can get charcoal as well. So here's another slide showing you palynology is the study of fossil pollen. And we can reconstruct then the whole vegetational history. And it's great because, as you know, pollen in the spring is everywhere. So you have lots of it. It's very resistant to decay, so it lasts. And it's tiny, so we can count 300 grains through time and get a good history. And pine, we usually find when it's drier, and hemlock when it's wetter. I don't know if you know, in the Catskill Mountains, there's a lot of hemlock where it's wetter. And these are other disturbance herbs that are from Europe. So when we see those, we know that Europeans were here. For the age, we know that marshes are great for dating because the seeds, the plants, are taking their CO2 from the air. And if you try to date a shell in the ocean, it's taking its food from the water, which could be old, right? Because there's erosion. But a plant in the marsh is taking it from the air, so we know that the dating will be good. And here's our other markers, ragweed for colonial impact. We also get isotopes, which I don't have time to get into, but it tells us about basically poop and pee and fertilizer, and then heavy metals. So let me just show you some of the pictures because I want to get through it. I know it's a lot to absorb, but just to give you a feel for what we do. So here's our core. We take little samples and we burn it. And what I'm showing you here, the red is the inorganic, so the sand, silt, and clay, and the blue is the plant and animal matter, which stays about the same. You can see through time. But the red, the inorganic, is really going down. And that's because the streams have been, hardened off to concrete. This is a busy slide. This is yellow bar, but it gives you, again, the top is 10 centimeters, the bottom's 2.15 centimeters. So a little over 2 meters. And this gives you the percentage, in this case, pine, the first one, of pine pollen through time. So when you see it start to decline, that's Europeans cutting down the trees. You see the same thing for oak. You see hemlock just get totally wiped out. And what you do see increase with this orange arrow is ragweed, really increases, and then declines in the 20th century when grass increases. And I'll come back to this. But it's a lot of information. These are deforestation herbs as well. So now we have a
Oh. Dr. Dorothy? Let's just give her a minute or two to reconnect. It might be the internet. Oh, Dr. Dorothy, we lost you there for a moment. Now you're back. Can you unmute yourself? Thank you. Oh, let me see if I can unmute. You're still on mute.
unmute. Now is it unmuted?
Now
Okay,
it's good.
great.
Yeah, now we hear you.
Yeah, I don't know why I lost, sorry. So Joko's now the highest elevation marsh, and it's the best preserved. Here's the analysis for this, the loss on ignition. We burn it, and you see that it's a lot more organic up here than it is down. This time we went down to 4 meters. We need more dates, but you see the same pattern. If we separate the blue, in this case, is the mineral, and the green is the organic. So we're getting the same pattern. And the pollen basically is giving us the same pattern too. Our date here is a little bit older, but basically you can see around 115 centimeters, the Europeans came and cut down the trees again. So we also then get the lead and copper, heavy metals, and you can see the big increases and declines. The increases are the industrial age. So we've dated that with isotopes so that we know 1839 exactly. And we put it together with these other pollen records and the organic and inorganic. And we see that we're getting the same pattern in all the marshes. The top one is Joko, the bottom one's yellow bar. So when we put it all together, we published this paper in 2018, we see a big decline in the inorganic since the 1800s, which we talked about before being due to the dredging and the hardening of the shoreline. But we also see, and that's this big decline, we see an increase in the organic, and we think that might be due to higher CO2, maybe the plants are growing better, or nitrogen fertilization, which is higher, but through time, it will probably degrade more easily. And that will cause the marshes not to keep up with sea level rise. Because when you give them higher fertilizer, they actually fall apart more. So that's the story for Jamaica Bay. We see the heavy metals increasing, and I forgot to mention that when we had the 1972, I think, Clean Air Act and Clean Water Act in the 70s, we can see that decline in the heavy metals. You see the zinc, lead, and actually copper all decline due to federal legislation, which is great. Then if we go to Piermont, which is right next to Lamont, I'll probably go through these quickly because I want to make sure I get to your questions. But we did the same thing, right? And we can take cores. Unfortunately, this marsh is all covered by an invasive plant called Phragmites. This is what it used to look like with the nice Spartina, the native vegetation. And here's the Spartina coming behind it, which can be 20 feet tall. So again, we did the pollen. Here we are pushing down. We have gone over 14 meters of peat in this marsh. So that tells you how much carbon it's sequestering if we measure, you know, what the carbon content is. And what's sad about this marsh is that you used to be able to walk out on it, and it's a wonderful environment, but now you can barely walk through it. You can see, and you have to canoe through the channels. But here's the pollen diagram again. And the yellow arrow here is like the orange one. So we see European impact with the decline of the trees, ragweeds rise, and again, the 20th century, there's some reforestation and grass increase. But what surprises here was the medieval warm time was here. We saw tons of charcoal. So when Europe, you know, they were growing grapes in Iceland, we had drought and huge fires. And actually, this slide shows individual species going down, the wetter species during that time, and the charcoal increasing. We also did X-ray fluorescence, which gives us the heavy metals again, but it also gives us information from the uplands. So titanium and potassium are two elements that come in with erosion. And when the colonists came and cut down the trees, there was a lot of erosion into the marsh. So it's sort of the opposite of Jamaica Bay, where we saw those marshes are starved of sediment. These marshes had a lot more sand, silt, and clay coming into it because of erosion. And that's paralleled by our burning it and seeing the organic, which is gray, and the inorganic. But then it sort of stabilizes towards the present. We also see the salt front, which is interesting. You know, the heavier salty water in the Hudson sinks. And when there's less fresh water coming down from all the streams, the salt front moves further north. So we see the samples during that drought get much saltier using the XRF machine. This is Tim Kenna, another scientist I work with at Lamont, measuring it. And these spikes are the times when it's really salty, and the medieval warm time is one of those. So climate changed. We had big droughts, we had fires in the past. We know one of the things I'm worried about with droughts is that New York City's water supply is really at risk, because only in the 60s, in 2 years, it went down to only 25% capacity. Tree ring records from the area also show us we've had big droughts in the past. And the Catskills, of course, are our 90% of the water supply, but predictions are that we could have future droughts, although lately we've had more rain. So it's just something to think about if we do And what happens to the fish? This is a fish scale we find in our cores. We know that when you have low flow in the river, there's more algae, autochthonous food. So algae, and the marshes are less flooded. The fish don't have as good reproduction, and you can have die-off. So that's a concern for the future. Again, we did the same thing. We burned it. You see this increase in organic matter towards the top. In order to get the carbon content, we multiply the organic by the bulk density, the mass over volume. And we also see a lot of heavy metals in the top of the marsh, the top meter. And that's one of my biggest concerns, because if we lose the marshes, these heavy metals are going to go back into the estuary. And that's really bad for all the animals and for us. Here's all our dating of seeds. All these are dates at different depths. And we come up again with an age profile. These anomalous dates you see on the right, these younger ages, if we're going back, this is, in this case, 0 is the present is on the left side of the x-axis, and deeper in the core is on the right. And the age goes from 0 to about 2,500 years. But you see, sometimes we got younger ages, and that's because it's right at the core break. When we bring the core up, sometimes things get sucked on there. And so we get we threw those out basically because we get a younger age. But now we multiply, we get the sedimentation rate over time from the age, and we get the bulk density after we burned it. And that gives us, along with the pollen, here's the pollen again, and the heavy metals. You can see here these increase in the heavy metals again, and then their decline. It's really a timeline of change that, again, we can interpret and understand what humans have done in this environment. And in terms of the carbon through time, we see that the medieval time had very little carbon. This is grams per meter squared per year, the carbon flux. And that's because most of it burned off, we think. In the Little Ice Age, it was cold. The season was much shorter, and we had less carbon preserved. And then now it looks like we're going back up, but some of that may decompose. So we see in the past, we had more carbon back in time. In this case, this graph is 2000 AD, or this is close to the present. So sorry, the graph is turned on its head. We published this paper in 2020, but we've only gone back 2,500 years. We really need to go back to the bottom of Piermont Marsh, which is 7,000 years old. So the other thing they did was they hayed. They took off hay for the horses and the cows back in the old days. So back in here, you had carbon low because they were taking off the hay to use it. So I'm almost done. I just wanted to show you the projections for sea level rise for the future. This is a high, medium, and low. And our marsh is accumulating at this red curve. So between 2 and 4 millimeters a year. So it looks like it's going to be underwater, right? Unless we do something. And the thing that we should do is add sediment, because remember, Jamaica Bay was starved. If we add sediment, that helps hold the marsh together, and we can keep up with sea level rise. This is what they did in Jamaica Bay. So we know we're having lots of climate change. We just this last weekend had huge floods. Here's another remnant marsh we're working on in Pelham, New York, if any of you know that. And we're trying to understand again how best to preserve it. So these are the conclusions about the carbon, the rates, and adaptation, how we're going to keep carbon in the ground. And that's a real application for sustainability that I never knew that I would get into when I started this, as you know, with the interest in botany. The other thing, if we open some of the dams, and the Hudson has a lot of dams, there are over 2,000, we might help to get sediment. So that ends my talk, and I want to give you time. And here's some of the questions that were sent to me, but I'm happy to answer more questions. And I don't know whether I should just jump into that or wait for questions about the talk. So you guys decide that.
Dr. Dorothy, thank you so much for this fascinating presentation. You know, with our summer program, we talk a lot about climate storytelling. And as you were sharing all the findings in your work, I was thinking, you know, that sample, it tells literally just that hundreds of years of history. So it's like it tells a story on its own too, which is just really, really fascinating. And also highlighting, you know, we really reminding us that we really are a part of an ecosystem, right? So it's not just that it's, you know, taking the carbon sequestration, but also, you know, when the trees were cut down, the different allergies and what implications that have for our, you know, health or and the land loss. I mean, this is really amazing. Thank you so much for sharing your work.
Oh, sure. No, I think everything's connected. That's what you see the older you get, right? Everything's connected. And so the more you discover, the more you realize how little you know and how you want to learn from other people. I think that's one of the biggest takeaways for me.
Yeah, no, that's great. So I do want to open up to our students for, I know you guys must have a lot of questions. So please, you know, any questions you have about the presentation, and even I know Dr. Dorothy might go into this, but even about her work and her profession, you know, feel free to use the chat. You can also unmute yourself and ask questions. As our students are coming up with the questions, maybe I could also go ahead and ask a question. I don't know if Dr. Dorothy, can you hear us? I think she may have dropped off with the internet. Tim or Radhika, do you see her? I don't see her on my...
I don't see her yet. But I just wanted to comment while she comes back with us. I don't know how many of us get a chance to go to our wetlands and explore our neighborhood, or do we just go to our malls and more, I guess, theme parks and Disneylands? And can we change that and see what we find in our neighborhood and what we learn from it? Because what I found interesting was that this interest came as a way of exploration. She never thought that she will be a botanist, and she never thought that she will, you know, work on these topics, but it just happened that she was exploring her wetlands, and she was observing things. So I just wanted to ask anyone here if this idea of exploring your own neighborhood, your wetlands, whether it's a lake, sometimes it's even your yard, looking at things that move very slowly, so you have to be very still and very silent when you observe things. Has that happened to you, and do you do that in your pastime?
I think maybe I can share by starting. I feel like just day to day, I use a lot of the day-to-day busyness as kind of an excuse to not take that time, because I feel like now it doesn't matter what age group you are, right? I think it does take a lot more intentionality to make that time in your schedules, right? So thank you for asking that, Radhika. I feel like unless you're intentionally carving out time, it does become harder to do. And yeah, I think that's a great point. She was observing plants and then she got into this now to the science of where just this, sample tells hundreds of stories, that's really something. But yeah, I want to give our, all of you time to respond to Dr. Radhika's question. So please feel free to use the chat, or if you can unmute yourself or come on camera, we would really like to see you and hear you too.
Yeah, why is, by the way, only 3 people on camera and that to us? What's happening with the rest, guys? We want to see you and we want to interact with you. We don't want to be seeing blank screens. So come on. It's okay if you're in your bed still, it's fine. Great.
Thanks. Yeah, thanks, Sana. Thanks, Paswar. Thanks, Advai, for coming on.
I would agree with what Hayden said. I think everything in life moves so quickly. And that's often used as sort of an excuse to really not really pay attention to the minute sort of details of what's going around in our environment, and to really, I guess, set more longer term and more broader scale, I guess, settings and goals in mind. But I think just the scale of what she's the professor's doing in terms of her research is just so impressive.
Nice.
Yeah. Oral has the hand up. Oral, go ahead.
Hi. So I have a balcony in my room, and sometimes when I'm studying, I notice myself looking over and seeing birds coming and sitting, or little bugs just crawling around. And well, it is distracting, but it's also nice to just look at nature for a while.
Thanks.
I have a 11-year-old at home, and every time she goes out, if there is a bee, she yells and comes inside because she doesn't like bees at all. She doesn't want to be with them, and she feels, why are all these bees in my house? So I have to keep telling her, this is their house. This whole earth is their house. We have to learn how to live with them, and we need to learn to see what they do, what they observe. So just going back to Dr. Peteet's message on observing things, exploring things, and see how you can your interest changes, I think is something which I can definitely relate to. Dr. Dorothy's back again. If there's anything that you want to share, or if guys have any question.
Yeah, sorry, I don't know what happened, but I'm back.
No.
Yeah, any questions?
Dr. Dorothy, while you were offline, Dr. Radhika was sharing, how it's so interesting how your entire career came about from, your interest in plants, kind of, and, we just don't know where things will lead, and how we really need to value, examining and exploring our immediate surroundings, which we often forget to do, or we get too caught up in our day-to-day to really do that. So we were discussing that a bit, and some of the students were sharing, what they have done, any of the outing and explorations that they have done around their neighborhoods or environments.
Yeah, I think it's amazing what's just around you. I mean, I was amazed to find out the other day that salamanders can live 20-some years, 26 years, one salamander. And they change colors and go back to the pond, and we take for granted, we think we know things, but we really don't often about our environment. And I never thought I would be working on carbon storage. It's amazing where things can lead you. I should also point out, I don't have the skills, but a lot of my students are learning ArcGIS, and that's so valuable to try to map the area, and then we can calculate from the depth. So that's I should have put that as a skill. That's super important. But I don't have it.
Our students are super lucky, you guys. I hope you know, and it's not coming from the program team, so it must be real coming from Dr. Dorothy. You guys are learning ArcGIS, right, through this program.
That's great. That's really great. Yeah.
There There's a question in the chat room from Lara, which is, what is the risk of building over the wetlands?
There's a lot of risk, and that's what I see when I go back to Queens. There's a wonderful wetland, but I saw they're building a golf green over it. And they're putting big Amazon warehouses on wetlands. And what that does is it stops the accumulation, of course, and it really ruins the whole wetland for any future carbon storage, and it may contribute to erosion of it too in the long run. So we should protect them better than that. You know, they also, I think, are probably really important in cleaning the air, just like any plant, right? Trees help clean the air by taking in CO2, and I think marshes do the same thing. And then there's another question, why did you choose JFK? We're doing this up and down the Hudson. I chose JFK because it's close to, it's a national park. And so it's an important area that protects New York City. And we just wanted to know what's going on there. Why are they eroding so fast? And it turns out, you know, they're really starved from sediment. But I've worked in Alaska for 20 years too. I love wilderness. So I fly back and forth, but I live here. So I'm curious about, you know, the wetlands around me. And then the third question, choosing locations, a lot of it's just serendipitous. I would love to go to Iceland and work on some bogs. I've worked, like I said, in Alaska. I worked in Russia when I always wanted to compare the Arctic Circle on one side, you know, Russia compared to the US. So back in the 80s, I just wrote somebody and went there and have a record from there. But it's often been serendipitous, I would say. And a lot of science is, you know, it follows your interest, I think, a lot of times.
Dr. Dorothy, in your presentation, you also mentioned, you know, to see more or to see even further down in past history, you kind of need to, you know, get to the bottom, right? With current kind of tools, and I'm so not literate in this area to know, but how deep can you go to collect the sample with the current tools that are in place for this kind of sample collection?
Well, I think we're kind of in the primitive dark ages because we do everything by hand, but it also allows us to get to wilderness. So the deepest I think I've ever cored is about 20 meters, so over 60 feet. That's as much as we can push. But we also can do that underwater, right? So you can have 10 meters of water on top. We core lakes in the winter. I could show you a whole nother presentation on lake records that we've done. And around here, you know, the ice sheet came right to the New Jersey border and goes up across. So we have a lot of records. I've cored about 7 to 10 sites along the glacial moraine where the ice sheet stopped right across Staten Island. And when you're doing that, you're coring, and then you hit rock that the glacier left. It's called till. And so we have a lot of records. But in theory, there's a place in North Carolina I want to core that could go down 30 or 60 feet, but I would have to get a drilling rig to help. And you just reminded me I need to do that because we can't push that far and pull it up. Yeah.
I have a question if there's
Sure.
more time. So you mentioned early on in the presentation that these areas of wetlands and blue carbon areas are better at sequestering carbon than even forests.
Right.
So I just wanted to know if you've seen, maybe in your experience, is it easier to maybe control and expand these blue carbon areas than it is, and maybe it's cheaper to do that than it is to do forests, or is there not really a difference in like cost of implementation?
That's a very good question. And, you know, I'm very ignorant in terms of the economics of things and policy. I'm trying to learn more, but it's the whole carbon game is sort of like a Wild West, how much value people are putting. I would like to learn a lot more about it because I think it was very expensive to do that dredging and spray the couple of islands they did in Jamaica Bay. And I asked if they're going to continue because otherwise they'll lose them. And they said, well, it was very expensive. So, you know, everything's relative. But I do know that the economic papers that value wetlands have, I think, value them now 50 times more than they used to, based on all the things that they found out that they do, because we just were ignorant before. But it's also land values. So a wetland protecting New York City is deemed more valuable than one protecting a Georgia island, right? That doesn't have a big city. And in my mind, that's not exactly fair because the great blue heron doesn't distinguish maybe between the two, right? So, but it's a good question. I think we should pour a lot of money to preserving wetlands. Yeah.
Sounds good.
We have two more questions in the chat.
Okay.
Is your work in depositing inorganic materials to protect the wetlands from rising sea levels open to the general public? Can people volunteer to participate in this work? I think that would be extremely helpful as it would allow the scope of the project to be expanded.
That's a great question. And where the public really can get involved is in replanting, because sometimes it's called thin layer placement. They spray sediment, but then you need to replant. And the public has been involved in that. But right now we're just trying to get the Army Corps of Engineers to understand that we need to put sediment because they a lot of times
If Dr. Dorothy gets disconnected, I can record the chat questions as well, and we can post in the Google Classroom.
That'd be great. Thank you, Tim. Oh, she's back.
Yeah.
Okay.
Sorry, what I was saying, first we had pushback that they couldn't use sediment in the river because it was contaminated. Well, the marshes already have contaminated sediment, right? So that argument didn't make a sense. But I think, yeah, it would be great if the public were involved to help for sure. And then the last question, no, I don't think taking samples has much negative effect. It's, you know, if there's a big marsh and you're taking a core that's very small, only 2 inches across or 3 inches, I'm sure for one individual crab who loses his spot or something, there is, but I think overall the analysis is valuable. So, you know, I don't think it has much negative effect on the whole ecosystem because it's such a small core that we take. Yeah. These are great questions. Anybody else?
Any other questions? Dr. Dorothy, you referred to this as just one question, burning question, so I'll ask, but you mentioned, you know, different losses of like wetlands that definitely affect, you know, how much they can absorb the carbon or not. But given the current state of our, you know, air where there's so much carbon dioxide, is there a point where scientists are now getting worried that they can't actually sequester or hold carbon, or how does the process look for that?
No, in fact, I mean, the land can keep taking up tons of carbon, right? But we're cutting down forests so much, whether it's the Amazon or Or, you know, the Canadian fires, they're burning CO2 back to the air. So one of the big pushes, and we're going to try to hire someone here at Lamont. There's nobody who works on crop soils, but there's a lot of carbon that can be stored in, you know, all the agricultural areas. If you don't plow them up all the time and let carbon decompose, because if you help to mulch, you know, and put more organic matter into the soil that keeps it there, it's a big potential carbon storage for the future, is just in agricultural soil. So I think that's one of the big advances we can make, as well as, you know, keeping our wetlands. And as somebody mentioned early on here, you know, we can help wetlands grow where we don't have them, just by putting the right mixture of things. So there's a lot we can do, I think, and there's no end to what we can do, I think, as well as trying to stop using fossil fuels and putting more CO2 up there.
Thank you so much. On that
Sure.
hopeful note, in the interest of time, we'll close the presentation here, but just round of applause for Dr. Dorothy.
Okay. Well, thank
much.
you all for coming. I applaud you for being here
Thank you so
and
much.
listening. Thank you.
Thank you. So for those of you, I mean, I don't think we'll have time for maybe a full breakout group today, but maybe we could just do as a group without going into breakout rooms. How does that sound, Tim? Maybe instead of the breakout rooms, we just do it because we have about just 5 minutes. I'm just trying to share my screen. You know, one of the things that we're doing in this program is not just that you learn the science bit or just the geospatial bit or the different motivations on why we're all interested in sustainable development, right? We want to bring all of those different pieces together and also focus on wellness. That's not talked about as much, but in the recent few years, one of the things that we have been working on at our center and with our partners is really looking at sustainable development with also the lens of wellness and overall well-being. So in order to do that, we wanted to do this as a group. Let me just share with you here. Can you see my screen? So today we were going to do this in breakout groups, but maybe we can just do it if you want to put it in the chat or if you want to unmute yourself and share. Today's theme being gratitude. So write 3 things you are grateful for today. I'm sure you've seen this exercise many times in different activities, different programs, but just simple act of remembering what you're grateful for is a big part of wellness. So yeah, if you don't mind sharing, it doesn't even have to be 3. Maybe it could just be one thing that you're grateful for today. You could put it in the chat or unmute yourself and share. That would be great. So I'll leave that all to you. And we could do that just for the next 5 minutes until we close. And as a last reminder, please do check out your Google Classroom where you have an assignment this week on the 9 planetary boundaries, learning and reading about it on your own under week 4. And then our data session is Thursday, 11 a.m., same time, same Zoom link. So we'll see you on Thursday. All right, so some of you have shared in the chat. Let me just bring it here on the screen. I'm grateful for my family. I'm grateful for sunny weather, good friends, and good food. I love that. Today, I'm grateful for family, clear air, quality, and health. Oh, I love that. You know, after seeing how the air we were affected, we couldn't leave our houses with the smoke from the Canadian wildfires. Yeah, even air that we're breathing, we cannot take for granted. So I'm grateful for my parents, my health, and my education. I'm grateful for being here, and we're grateful you're here. So yeah, grateful for all of you being here. I'm grateful for family, friends, and this earth. Grateful for family, health, and the opportunity to be here. Grateful for this amazing environment Almighty has provided us. Grateful for having my family and friends with me by my side, for having the wisdom to change whatever it is, and for adventure and fun in life. Thanks for sharing, guys. Feel free to keep adding them. Are there any questions before we close too? It could be, about our session program. Yes, Tim, go ahead.
Yeah, I was going to say, I know some of you had mentioned in the beginning of the meeting that you hadn't attended the last Thursday session, so you hadn't sent your email and chat. So anybody not really last call, but last call for today, if anyone doesn't have an email from the Esri licenses or hasn't sent me the email or hasn't responded to the survey, either chat to CSD education team or chat to Timothy Mentor and share me your email and I can add you. Just putting it out there in case anybody hadn't.
Thanks, Tim. All right, so I think we're closing for today. We'll see you on Thursday at 11 on the same Zoom link. See you on Thursday. Thanks, everyone.